going to wait 1 minute and then we're going to start. So you all went through the syllabus, right? Actually, you read it.
Do we have to have our backup?
You don't need to have today. Today we're gonna go through the syllabus, safety thingy, like that, and then I think your lab gonna start from next week. Unit lab from next week. All right. So now we're gonna start. So this is gonna be quick recap of ZenChem. This is a revision, right? So if you have any questions, just feel free to ask me. All right. So now you know the difference between cells and orbitals, right? So now you are doing organic chemistry. So you're going to deal with hydrocarbon, right? So hydrocarbons are made from carbon and hydrogen, right? So now carbon going to be the focus over here. So now how many cells and how many orbitals you're going to have for carbon? Can you calculate that? Let's do it, right? This is the basic thing. So cell, that's easy. So I have carbon over here. So I'm gonna have N1 and then I'm gonna have N2, right? So that's the cells. You have two cells in carbon. One is noted by N1, other is noted by N2. These two are cells. Okay? So that is clear. So it is also called Bohr orbital. Bohr orbit. You can call that. That's fine, right? So you have N1 and N2, right? So now the question is, how many orbitals you're gonna have? So now when you deal with orbital, you're gonna be based on given N value, right? So you're going to have the one set of orbital for N1, you're going to calculate for that. And then you're going to have other set for N2, right? So you're going to have two sets of orbitals there. So for N1, so orbital is going to be L, right? That's the notation of that, small l. So what is going to be the value of a L when N is 1? So the value is going to be
0.
starting from 0 all the way to N minus 1. That's going to be the value for that, right? So N is 1 over here. So 0 to 1 minus 1, 0, right? So this is going to have only one value, that is 0. So when you have 0, the notation is 1s. That's the notation of the orbital. So for N1, you're going to have 1s orbital for carbon, right? So now you can do similarly for N2, right? So what is going to be for N2? So you're going to have, they're going to have the green color over here. So for N2, I'm going to come down over here, right? You're going to do the same thing. So L going to be 0 to N minus 1, the same formula, right? So now you have N2, right? So 0 to 2 minus 1, which is 1, right? So you're going to have 0 and then you're going to have 1. So now you have two orbitals over here. Before you had only one. 1s, right? So now you're gonna have for 0, there's s orbital like before, but it is for n2, so we're gonna write 2s for that. Right? So before you have 1s, now you have 2s, the same s orbital. 1s is inside n1, 2s is inside n2. That's the notation, right? So now 1 gonna be p orbital, so we're gonna have 2p over there. If you have 2, then gonna be d orbital, 3 gonna be f orbital, like that. So L value of 0, 1, 2, 3, if you have like that, so L 0, 1, 2, 3, you're gonna call S, P, D, F, G, F, something like that. Right? So that's the notation of that. Okay? So now you know the orbitals in carbon, right? You need this when you deal with hybridization. You're gonna mix these orbitals together to form the hybrid orbitals. So you're gonna mix 2s and 2p orbitals to have the new set of hybrid orbitals. So you need to know how many orbitals there are, right? Good? Clear? Alright. So now, the one more thing. So whenever you see 2p orbital, so you're gonna, how many boxes you have? So that's the one you need to know, right? So for 2p, you're gonna have that many boxes over here. So if you go with the magnetic quantum number, the value gonna be from minus L all the way to plus L, right? So this gonna come with MEL, magnetic quantum number. So this gonna be minus L to plus L values. So you have 1 per P, right? So you're gonna go from minus 1 all the way to plus 1, so you have 0 in between, right? Those 3. Magnetic quantum number. So the notation of that is Px, Py, Pg. So you have the 3 subclasses inside the p orbital. So for S, you have only 1, right? So minus 0 to plus 0 is just 0, right? So you have 1 for S orbital, you have 3 for p orbital. So these are noted by 2px, 2py, and 2pg, right? So these are called the degenerate orbitals because they have the same energy, right? So x, y, and z all gonna have the same energy, so these are degenerate orbitals. Okay? So now, once you know that, we're gonna review a little bit about the electron configuration. So you have 2 ways of writing the configuration in ZM class, right? One, you're gonna write all the orbitals you have in the atom and then fill the electrons based on the capacity of the orbital, right? So for example, carbon, the same example, if I write that, so what's gonna be the orbital state for the carbon? You had 1s, right? And then you had 2s after that, for n equals 2, right? And then you had 2p after that. So these are the orbitals for carbon, right? So now, what is the atomic number for carbon? 6, right? If you see the periodic table, you're going to see number 6, atomic number, right? So now you're going to fill that 6 electrons in these orbitals, starting from the lowest energy orbital all the way to the highest one, okay? So you're going to put 2 over here, you're going to put 2 over there, and then remaining whatever you have, 2 gonna be over here, right? So this is one way of writing the electron configuration, right? The other way is, if you have the noble gas before that, which is helium before carbon, right? So you can write helium for this thingy over here, just replace with helium. So whatever inner electron or core electrons you have there, you're going to write the noble gas for that core, that many core electrons, right? And then whatever the balance remaining you have, that is the outermost cell. No matter how many orbitals you have, you're going to write after that. So 2s2, 2p2, right? So that is the another way of writing it. So you can write either way. So the point is, our focus is going to be this one, the valence, because all the bonding, other properties we're going to see based on that, valence electrons. So that's the focus. So we're going to just separate the core electrons from the valence, and we're going to focus on the valence electrons, right? So that's the reason why here, whatever you see, all are valence electrons on there in the picture. You don't have any core electrons on there. You have core electrons for all these atoms, but these are separated. Okay? So this is the electron configuration, right? So now you have few principles for different properties. So one gonna be the Pauli principle. So do you remember what this means? What does the Pauli principle say? Each orbital can have 2 electrons if they're with the opposite spin, right? Okay. So let's say helium, simple one. So you can write the orbital for that now, right? You have N1 cell only for this. So you're going to have 1s orbital, right? So you're going to have the 1s orbital. I'm going to write it this way over here, 1s orbital, right? So for that, what's going to be the quantum number? So you're going to have N1, of course. That's the principal quantum number. You're going to have a L0 because L is 0 to n minus 1. So you have one value, right? And then you're going to have a ML minus L2 plus L. That's the value. So minus 0 to plus 0, you're going to have only 1 0, right? And then you're going to have MES, right? So what's going to be at that? So that's what it means. This is another way of saying that. Okay? So if you have the same set of 3 quantum numbers for any electron pairs, then the 4th one must be different. So you have 2 electrons there, right? So one is like that, other is like that. So one is up arrow, that is plus half. Other going to be the down arrow, that is minus half. So that means MS should be different. One is plus half, other is minus half. Right? If you want to say other word, then you can say in any given orbital, if you have 2 electrons, they cannot have the same spin. They're going to have the different spin. One going to be the clockwise, other going to be the counterclockwise. Or plus half, minus half. Up arrow, down arrow. Right? That's what it means. Okay? So this is the Pauli principle, right? Other going to be the Aufbau principle. So what that means? Let's say the example of carbon. They're going to be easier, right? So when you feel the electrons in the carbon orbitals, then based on the above principle, what do? So you feel the 1s orbital first. And then if you have any extra electron, you're going to go to 2s. You're going to feel that. If you have more electron after that, you're going to go to 2p and then feel that. If you have more electron, then you're going to go to 3s. Something like that. Right? That means when you feel the electrons in any set of orbitals of given atom, what are you going to do? You're going to feel based on the energy of the orbitals. You're going to feel the low energy orbital first, and then you're going to go to the higher energy orbital. Right? That's the above principle. So that's what it says, right? And Horn's rule, the next one. So what that means? Can you remember? Degenerate, right? So it's gonna be applicable for the degenerate orbitals, like p orbital of carbon, right? So here I wrote p2, right? You have 2 electrons in p orbital, but if you write in the form of box, how many boxes you have there? You have 2px, 2py, 2pg, right? That's the same thing for p orbital, 2p, right? So now the question is, I have 2 electrons there. Where should I put 2 electrons? Into px like that?
No.
Or are you gonna write 1 each, something like that? That's what Horn's rule means, right? When you have the same energy orbitals together, that is the degenerate orbital, you're gonna feel the electron singly first. And if you have extra after that, you're gonna start pairing them, right? So that is called the Horn's rule. So we're gonna feel singly. So the second one is right. 1 electron in 1 box. The first is not right. Right? Based on Horn's rule. Alright? Good. That's a quick recap, right? Alright. So now, bonding. Once we know the electron configuration, in particular the valence electrons, that's the focus, right? Forget about the core electrons you have there, and you know all the principles there. Now we're gonna go towards bonding, right? So what is bonding? So the bonding is making the octet state for any atoms in the molecules or compound. Right? So if you have all atoms with the 8 electrons on the outermost cell, that's the octet, right? So that's the bonding. Right? So if you see periodic table and see the valence electrons, say for example lithium, you're gonna have only 1 electron on the outermost cell, right? And for beryllium, you're gonna have 2. Carbon, we saw 4 already, right? So 2 gonna be the core electrons. We are not showing that. This is only the valence electrons, right? So you have the other atoms there. Sodium, for example, you have 1 electron in 3s orbital, right? N equals 3 cell. So these are the dot structure, Lewis dot structure, we're gonna call that, because this is helpful to decide what type of bonding you're gonna have to form the compound or molecules. Okay? So with that, so you're gonna have the octet formation, like say you have the molecule compound. This is compound, right? NaCl. This is the product you have. So if you see before combining them, what's going to be the sodium configuration? This is going to be the before combination, right? So this is the before bonding. So you have the separate sodium there, you have the separate chlorine there. So for chlorine, how many electrons going to be on the valence cell? 7, right? So 7 are shown over here, the dot. So now, you want to make octet for both sodium and chlorine. How is it going to be possible? If you share electrons between them, do you think going to be possible? Sodium going to give 1 electron and chlorine going to give 1 electron to share them. So sodium going to have only 2 to share with the other, right? So sharing is not possible. So the other way of making octet is losing 1 electron by sodium. So it doesn't have any 3N3 now. You're going to have N2, right? So you have the sodium there. So you have N1, and you have N2 there, and you have N3 there, right? So you have 1 electron on N3 valence. So if it loses that, then this cell doesn't exist. So now you have N2, which is already filled, that's octet, right? So that's why it's gonna lose electron, and then the chlorine. So you have the chlorine there. So it has same number of cell there, N1, N2, N3, right? At the beginning it has 7 electrons. So 1, 2, 3, 4, 5, 6, 7, right? So now it's gonna have 1 electron given by sodium, so it's gonna be 8, right? So if you take this electron, this one over here, then total gonna be 8, right? Okay. So that's how this bond is formed over here. When you have octet, bonding gonna be there. So Na plus, it has 1 more proton than electron, so it is plus. And then Cl minus, you're going to have 1 more electron in chlorine than proton, right? So for chlorine, you're going to have proton 17. Now when you have the extra electron, you're going to have 18 electrons. So 1 more electron there, right? So that's why it is octet and Cl minus. So now you see the energy. So this is the focus over here. Why you're going to form bond between the atoms? To lower the energy, right? If it is in uncombined form, it's going to have the higher energy. So this is the energy you have, that one. So that's the energy before bonding, okay? And the energy over here, down there, that's going to be the energy after bonding. That's the reason of making bond. So it's going to be more stable, or the other way of saying that is it's going to have the less energy compared to non-bonding. So whenever you make the bond between the atoms, it's going to be more stable. That means you can have less energy. Okay? So that is called the energy profile or energy diagram. Okay? So you're going to see the same thing with the configuration. So this is how you're going to show. So you're going to have all electrons, which is 11 over here if you count them. You're going to lose this one. So you're going to lose the 3s1 out from there. So you don't have any 3s1 there. right? So you have up to n equals 2 cell. And then same for the chlorine. You have 17 total over here, right? So you're going to have one more electron from the sodium. So if you see 6 over here and 5 over here. 5 plus 1 is 6. So p orbital is completely filled, right? It's octane. So that's how you're going to make the bond, right? Good? Any question on that? All good? Let me know if you have any question. I can explain more. But make sure you know this, because you need this later on. Good? All right. So now this is favorite diagram, right? You see this in Duncan. So how do you read the values given over here and then guess the bonding type? So this is the electronegativity difference, right? So you can write delta En. That was the notation we saw before, right? So that difference is starting from 0 all the way to 4, 5, whatever value you have, right? What that means? If you have the value close to 0, that means the combining atoms you have, they are nearly same in terms of the electronegativity, right? If you have the more difference, that means one atom is more electronegative than the other one. Okay? So let me give you an example. So let's say you have H2 hydrogen molecule, right? So if you see the electronegativity table, you're gonna see 2.1 something, the value of electronegativity, right? So now, if you're gonna calculate delta En for the molecule, what's gonna be the value? Delta En. What's gonna be the value for H2 molecule? So let's say for hydrogen you have 2.1. Is that the difference? So you have two atoms there, right? You have two values, 2.1, 2.1. So you're going to take the difference of that. So 2.1 minus 2.1, what's going to be the value? That's what it means over here. Right? So for any compound, if you see the value nearby 0, or 0.1 something, right? So that means the combining atoms you have, they have nearly same value of electronegativity. Okay? So what about let's say 0.4 case, more than that, say 0.4 to 2. Let's say you have HCl as an example, right? So Cl is more electronegative, we know that, right? So Cl is going to have more value of electronegativity compared to hydrogen. If you take the difference between the En of chlorine and that of hydrogen, so you're going to have, delta En, that's going to be En of chlorine minus En of hydrogen, right? So you're going to see the value in the table. So you don't need to memorize anything. So just take the value and then plug over here, right? So you're going to have more than 0.4. You're going to have the difference of more than 0.4, greater than that, right? What that means? That means it's gonna fall somewhere over here in this range, anywhere over here, right? So still it is covalent. They're gonna share electrons between them, right? So for the hydrogen and chlorine, how you gonna share the electrons? So you have the hydrogen there, one electron, right? And then chlorine, if I show n equals 3 only, the valence electron, how many are you gonna have? 1, 2, 3, 4, 5, 6, 7. You're gonna have 7 there, right? So if you share that, these 2 electrons, then the hydrogen is gonna be complete. It has 1 s, so 2 electrons, that's the capacity, right? Chlorine has 8, so both are happy, right? So sharing of electron, that is the covalent bond, right? So the hydrogen, the same thing. If you make the bond between the hydrogen, so how is it going to be formed? Sharing the electrons, right? So both are covalent. Now what is the difference? One is pure covalent, other going to be the polar covalent, right? So the HCl is going to be polar, this one, and hydrogen is simply pure covalent, right? Any diatomic molecule, so say N2 or O2 or Cl2, all gonna fall on the pure covalent bond because the electronegativity difference is gonna be 0, right? That's the pure covalent. So any covalent bond between less electronegative atom and the more electronegative atom, like HCl, NH3, right? HF, something like that. So those are going to be polar covalent. Both going to share electrons, but their electronegativity values are different. Okay, based on that, we're going to classify in these 2 groups, right? What about the ionic then? So this is obvious, right? We saw NaCl before. So you're going to have the complete transfer of electrons. Losing and gaining of electrons to form the bond, that is the ionic, right? If you calculate Den for that, of course you're going to get more than 2. So it can be any value after 2, more than 2. So any value of difference more than 2 is going to be ionic bond, right? So that's the type of bond you have. So ionic, covalent, and for covalent you're going to have 2 classes, pure versus polar, right? So for hydrocarbon, so now if you go there, later we're going to see different hydrocarbons, like say you have CS4 as an example. This is methane, carbon and hydrogen, right? So now what do you guess? This is going to be pure covalent or polar or ionic? Take a guess. Don't do it. If I make it wrong, I gotta clarify it. What do you think?
Polar.
Polar? Yeah, nice guess, but it is going to be pure. So if you take the difference, it's going to be slightly less than 0.4 or something like that. So it's going to be borderline. So it's going to be pure covalent, right? But if I do CS3Cl, for example, so now I have the carbon and chlorine there and other hydrogens, right? So now if I do this, it's gonna be polar now. Why gonna be polar? Chlorine gonna have very higher value compared to carbon and hydrogen. So your difference, if you calculate that, carbon and chlorine, if you calculate this difference, it's gonna fall somewhere over here. So it's gonna be polar bond, right? So for hydrocarbon, if you have the functional group, which is non-carbon and non-hydrogen, you're gonna have different atoms attached there. So they're gonna give the bond polarity. You're gonna be polar compound there, right? From the polar bond. Okay, so that's the direct application. We're gonna see again and again and again that, right? So now you know the difference between the pure covalent and polar covalent, right? Good, yeah. No, you don't need to memorize it. So for the electronegativity values, so you're gonna have table if needed. You don't need to memorize it. Okay. All right. So now ionic bonding. So you already know that, right? So I don't need to talk that. So I'm gonna skip this. So normally you're gonna have the metal and non-metal to form the bond, right? So metal gonna be any transition metal or the first and second column metal, and then you're gonna have the non-metal on the right. So if you have the combination of these, you're gonna have the ionic compound. So metal gonna lose electrons all the time, and then non-metal gonna gain that lost electrons, and then you're gonna have the ionic bond. Okay. So covalent bond. So you're gonna have between non-metal, right? So those yellow colors over here. So these are the elements that are gonna make the covalent bond. Okay. And then the Lewis structure, now you already know that. This is dot structure, right? You're gonna have one dot for one electron, and then you're gonna focus the valence electrons only, right? So that's the one. So let's see one example. It's gonna be repetition. Say you have CS4, methane, the simple hydrocarbon. Okay. So what are you gonna write? You're gonna write the dot structure for carbon, which is this one. You're gonna write that. And then hydrogen, you're gonna have only one, right? You need 4 of them. So you have 4 dots, right? And then when you make the bond, so you're gonna share 1 electron with 1 hydrogen. So you're gonna have how many? You're gonna have 1, you're gonna have 2, you're gonna have 3, you're gonna have 4, right? So you're gonna have the 4 bonds there. Okay, this is covalent bond. So if you compare the energy like before, so on combined state gonna have that energy. So this energy is energy before bonding. That is, you take the sum of energy of individual carbon and the 4 hydrogens, non-combined form, right? And then the other one over here, so that is the energy after bonding. So this is energy after bonding. So you have the methane, more stable than carbon and hydrogen uncombined. Okay? Alright. So the next thing gonna be the formal charge. So when you see the molecule, say for example methane, right? Let's talk about the same molecule, the easiest one. So if somebody asks, what is going to be the charge of carbon you have in methane molecule? So we're going to use the formal charge. This is one of the methods. There are many methods to do that. This is one of many to guess the charge on given atom. Remember, it is not for the molecule. On the given atom within the molecule. They are going to say that, right? So this is the formula you're going to use. So you're going to pick the atom of interest. And then for that atom, you're going to see the valence electrons. Let's say carbon, right? So you're going to know the valence electron of carbon, and then minus half of how many shared electrons you have with that atom, right? No matter what other atoms are, here you have hydrogens, right? So you're going to focus on the carbon, so one given atom. And then if you have any non-bonded electrons, you're going to subtract that, right? So now let's use the formula. So what's going to be the valence electron for the carbon? 4, right? You see over here. 4. And then 1/2 of how many shared electrons? So for each bond, you have 2 electrons shared, right? So you have 2 electrons over here, you have 2 electrons over there, you have 2 electrons over here. So for one bond, you have 2 electrons shared. So you're going to count all these shared electrons, not only that of carbon, all. Alright? So how many total? You have 2, 4, 6, 8. So you're going to count all. So you're going to do 8 electrons. And then any non-bonded electrons. So how many non-bonded?
0.
0, right? So you don't have any non-bonded. So 0. So now you're going to have 4. So 4 minus 4, 0. So normally when you have the pure covalent molecule, the charge on the atom is going to be 0. Alright, so that's how you're going to calculate. So now if you use the same formula, let's say for the chlorine. So what's going to be the charge for chlorine? You're going to do the same formula, right? So the formal charge for chlorine is going to be, what is the valence electrons? 17. 17 is going to be the atomic number, right? You're going to have 2, you're going to have 8, you're going to have 7 after that. So 7 is going to be the valence, right? So you're going to write 7 of that minus half. So what's going to be the shared electrons you have? How many? So you have 1, 2 over here. So one bond is shared with the carbon, right? You're going to count that 2 electrons. So you're going to write 2 over here. And then do you have any electrons there that do not form bonds?
6.
You have 6, right? So you have 1 pair, 2 pair, 3 pair. So you have 6 of them. So if you solve that, what's going to be the value? So 7 minus 1 minus 1 minus 6. So you're going to be 0, right? You're going to have the 0 charge on chlorine. So that's how you're going to do. So you're going to be for the atom within the molecule. You're going to do one atom at a time. Right? So for all, the formula going to be this one. Right? Good? Any question on that? Yep.
Did you get a 7 for chlorine?
7 for chlorine. So if you see the atomic number in the table, what number you see? You're going to see the chlorine 1,7 like that. Right? So now if you're going to fill the electrons there, what are you going to do? You're going to put 2 over here, and then you're going to put 8 over here, you're going to fill that, right? Like this. And then you have 10 gone, right? How many remaining? 7. So you're going to put 1, 2, 3, 4, 5, 6, 7. Or you're going to write in terms of orbital. What are you going to write? You're going to have 1s for this cell. You're going to have 2s and 2p for that one. And then you're going to have 3s, 3p, and then 3d if you have any, right? 3d. That's the orbital. Okay? So now you're going to put 2 over here, 2 over here, 6 over here. So you have 10 gone, right? And then 2 over here, 12. And then 5 remaining. You're going to have 2p5. So you're going to count this. So that's the 7 over here. Good? All right. Any other question? All right, so reactivity. So now, this is going to be same concept, it's not completely different. But so, what is the relation between the reactivity and the dot structure? Of course, if you have any unpaired electron at the dot structure, they're going to form to make the pair, right? To make octet. So, for example, if you have any anion, like this one, this is called carbanion, you have the negative charge on carbon. So you have carbon minus, so 2 electrons over here, and then you're going to have hydrogen like that, right? So you have the minus charge on carbon. So this is CH3 minus, okay? And then you have the plus charge on carbon. So if you don't have any electron remaining there with that, so this is just plus, this is carbocation or carbocation, whatever you can call. So this is CH3 plus, right? So if you have this plus and minus, then what do you think? They're going to combine to form the bond. This is like ionic bond, right? One negative, one positive. They're going to combine that to form the bond. So you're going to have the bond between them. So one has 2 electron deficiency, other has 2 electron more extra. If they share, they neutralize together, right? So they're going to make the bond. Okay? So they're going to be more reactive. So if you compare this with the neutral center, the charged one going to be always more reactive. So let's say you compare that with CH4. So for CH4, you're going to have all 4 hydrogen bonded there. So the carbon center, this is neutral, right? This is neutral. It doesn't have plus charge, doesn't have minus charge. So if you compare with that, neutral center, what about the charge center you have in the molecule? That's going to be always more reactive, right? So you're going to have the reaction and you're going to have the product formation after that, right? So if you're going to calculate thermal charge, you use the same formula, you're going to calculate, right? So it's not different. So for CH3 plus, you're going to have plus 1 charge. For CH3 minus, you're going to have minus 1 charge, right? So the same formula. The valence electron minus half times the combined or shared electrons minus unpaired whatever you have there. So for CH3 minus, you have 2 electrons not combined, right? So these 2 gonna be uncombined electrons or lone pair of electrons you have over there, right? So for CH4, CH3 plus, you don't have any, 0, non-combined, right? All right. So now the next thing gonna be the Vesper theory. Right? So here we're gonna see some shape of the molecule, and then you're gonna talk about the hybridization and molecular orbitals. So chapter 10, 11, yours in Kim 1. Right? So you're gonna deal with that. So when you use the Vesper theory, what is the use of that? Can you remember? So if I write H2O over here, what is going to be the shape of the molecule? Linear, bent, tetrahedral, right? So you're going to know the shape of the molecule, then we're going to deal with the Vesper theory, right? All right, so make sure you review that. We're going to continue from here. Probably going to finish on Friday. All right?